Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly Testing Tactics webinar series. Today's topic is turns ratio testing, principle, operation, and new measurement techniques. My name is Jamie Smith, and I'm the marketing manager for AVO Training Institute, a subsidiary of Megger. And I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read those questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NETA CTD and one PDH or zero point 0.1 CEU just for attending today. You will receive this in an email within about 2 to 3 business days after the webinar. And that email will also include a copy of the PowerPoint presentation and a link to a video recording of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. All right, our presenter today is Aaron Tucker, Megger Relay Application Engineer. And also to assist Aaron, we're going to have a couple panelists, Diego Robolino, Principal Engineer from Megger Technical Support Group, and Daniel Carreno, Megger Application Engineer. Okay, let's go ahead and get started. Thank you for joining us today, Aaron.
Appreciate it, Jamie. Good morning, good afternoon, everybody, depending on where you are in the world. Today, as Jamie mentioned, we're going to be talking about turns ratio testing, principle, operation, and new measurement techniques. So here's the agenda. Again, we're going to go over why should we perform transformer turns ratio? What's the benefit of doing this test? We're also going to talk about different designs and testing standards. We're going to cover the basics of TTR. We're also going to go over the vectors and the nameplates, kind of just give a breakdown of what you see when you're looking at a nameplate of a transformer and how that converts over to doing the TTR test. Then we're going to look at TTR testing techniques, different ways and applications. And then we're going to look at results and data from different tests that we've done and information that we've gathered from different types of testing techniques. And then at the end, we'll just cover a few of the Megger instruments that you can use to do a TTR, as well as other testing. So why perform ratio tests? Again, what's the benefit to us to do this test? So when we look at a transformer, obviously we have multiple pieces of a transformer. We have tank, we have windings, we have a core, we have bushings, have all these things. And this is obviously a very critical asset within a substation, distribution, anywhere in your power system that you have a large transformer or even a smaller transformer. This is the main source of the power that is being supplied to the load. So this is a very critical asset of your operation. And so what we want to look at here is we want to look at the windings as well as the core and the tap changer. We can do that with the TTR test, and we'll go into that here in a little bit detail. And we just want to talk about the other types of tests that you can do on a transformer outside of TTR. Obviously, we have everything from insulation resistance to power factor to winding resistance. Again, though, for this presentation, we're going to focus on transformers turns ratio. So why do we want to do this test? Well, we want to verify that we have the correct specifications of the winding configuration, the way that the core was done, to make sure that the core is still aligned with the windings so we don't get an offset on our ratio. We want to verify the quality of the manufacturing process. We want to make sure that it does have the proper displacement that it should have based on the vector diagram, based on the IEC number. We also want to make sure that the connections and the tap changers are functioning in the way that they should be. For trending reasons, we talk about when we commission the unit to when we do maintenance on the unit later down the road, we want to make sure that the turns ratio hasn't changed. We want to make sure that there's no issues with the tap changer not going to the correct tap, things like that. And then also damage. We want to make sure there's no damage that has occurred. So it's a very basic test, but when you're talking about shipping of a unit and it goes maybe coming from overseas, maybe coming from across the country, you don't know what kind of damage that the unit may have been susceptible to during that transit. So we can do a TTR and we can make sure that there's no movement of that core and that the coils are still intact as far as that we don't have any shorted turns. There's no openings. The tap changer still working as it should. It hasn't malfunctioned or hung up or become damaged. So here we have just a diagnostic chart. It just kind of tells you if you were to look for these symptoms, you could use this test to find those, and these are the recommended tests. So for like a turn-to-turn short, you can do a turns ratio. You can also do a winding resistance, and off the excitation current of the turns ratio, you can determine whether you have a turn-to-turn short. And so again, we're focusing on TTR, so everything that we're going to be looking at today is highlighted in red here. Everything from poor connections, core overheating, insulating damage. We can gather some of that information based on the TTR results, based on the excitation current, as well as the ratio. So testing standards. Of course, there's a lot of different testing standards out there, but for the ones that we're going to be focusing on for this presentation are highlighted here. We've got IEEE C5712. This is more for the design, the manufacturing side of the house, as far as the proper specifications for transformers, distribution, power, and regulating. And basically what we can take from that is that the windings and all the tap connections should be within 0.5% of the nameplate voltages. So that's our tolerance. So we're going to base it off of 0.5% of the measured transformer turns ratio based off of the calculated ratio. And so we can see of comparing the calculated ratio to the nameplate ratio, we can find that what our percentage is as far as our tolerance. And of course, we want to make it sure that it's no greater than 0.5%. And then when we talk about Y transformers, you've got a difference between phase to phase and then phase to neutral. So when the phase to neutral voltage is not explicitly marked on the nameplate, the rated phase to neutral voltage should be calculated. And we'll get into that a little bit as far as the calculations that it does by converting it from phase to phase or phase to neutral or phase to phase. So before we get too far, we want to talk about some definitions. T and R. So what is T and R? Transformer nameplate ratio is your line to line or your line voltage, whereas your phase voltage would be your line to neutral or your line to ground. So we're talking like a delta. Our line to line is equal to our phase voltage, whereas with a Y transformer, our line to line is going to be different than our phase voltage. We got TVR. This is the ratio between a specific terminal voltage of the high voltage winding to that of the low voltage winding. And then we have TTR, which is the physical number of turns on a specific high voltage winding to that of a low voltage winding. And then the measured voltage ratio. This is where you apply a voltage on the primary or the high voltage side, and you measure a voltage on the low voltage or secondary side. Here's another standard, IEEE C57152. This is the standard that a lot of people in the field use. Again, it talks about the same 0.5% tolerance level. And it talks about just the general principle is to obviously induce a voltage on the high voltage side and read a voltage on the low voltage side and compare that ratio. One note to note, a couple notes here. There are some exceptions when it comes to the 0.5%. You may see that there are different ratios per phase, but as long as they're not outside the 0.5%, then they shouldn't be discarded. And then another one is LTCs, or on-load tap changers, also referred to as load tap changers. You can see that sometimes the way that they are designed, that they won't have an equal number of turns per tap. What this does is make the voltage variation non-uniform. So, but as long as the extreme ends of that tap changer are within the 0.5%, then it shouldn't be. It should be considered good. And just another note is when people talk about they have a TTR meter or a turns ratio meter that they're going to measure the TTR of a unit, you're not going to be able to actually count or measure the physical turns of the transformer. And so that's just a note there that you're not actually measuring the physical portion of the transformer. You're using a conversion of what you've measured and converting it over to TNR, which then converts over to what's your ratio. So pulling out of the C57-152, we have a diagnostic test chart here. It's just these are all the different tests that you can do on windings, and of course we're going to highlight that we're going to be looking at ratio, polarity, and phase. And so polarity and phase relation tests are of primary interest, especially when you're paralleling or banking two or more transformers, and they're made to determine the angular displacement and relative phase sequence. And then we're going to look at excitation current. Now this is a low voltage excitation current test. This isn't the high voltage excitation current test that you can do with a power factor test set. Okay, if we go into the tap changer, we can see we have our on-load tap changer, or OLTC, or sometimes referred to as LTC, and then our de-energized tap changer, also referred to as our DETC. And so we look at these again. This is how we're able to verify that the tap changer, as far as the ratio is concerned, is operating correctly. So we can check the ratio there on both of those tap changers. And then if we look at NETA, also has ATS and MTS acceptance and maintenance testing, and they basically say the same thing, 0.5% tolerance level. And they also note that there's an optional test on smaller transformers that are below 600 volts and maybe below 500 kVA. So if we look at the basics of TTR testing, how do we do that? So again, we apply a voltage on the primary side, and we measure voltage on the secondary side. Now, for this presentation, we know that a primary and secondary, you can have different configurations, right? So you can have a primary could be a high voltage or low voltage, and your secondary could be a low voltage or a high voltage, depending on your configuration. Step up transformer, step down transformer, whichever way you're feeding it. But for this presentation, if I revert to saying primary, I'm referring to the high voltage side, and I'll just reiterate that as we go. But so again, we're testing the voltage applied to the high voltage side and measured it on the low voltage side, and then the excitation current is what is generated when we do this test. And for the calculation here, we can see that the number of primary winding turns divided by the secondary winding turns equals our TTR, which is also directly proportional to our voltage on the primary divided by the voltage on the secondary. And just a little note here is for all the measurements, we're just going to assume that there's no load. So with a no load voltage, the ratio is approximately equal to the turns ratio. Also, when we don't have a load, we'll have negligible impedance influence. So we're not going to be looking at losses and things like that when we do the test. So we talk about permeability. The high overall permeability is important to attain proper ratio and therefore transformer efficiency. So if we can see here, we've got the construction of a basic transformer. We've got our high voltage winding, we've got our low voltage winding, we've got the spacing in between there, we've got press boards, air space to allow for if it's an oil field transformer, for the oil to come through, and of course we have our iron core. And any free space between the core and the winding is going to affect the transformer performance by lowering the cumulative permeability between the primary and secondary, or the secondary or primary and tertiary winding. With that being said, power transformers require gaps between the core and the associated windings, as we mentioned earlier, for cooling purposes, whether it's air or oil. And the tighter those windings, and you'll see the difference between maybe a large transformer to a small pad mount transformer is going to be how tight the windings are, which is also going to equivalent to a lot better mutual inductance and better coupling. So if we go into vectors and nameplates, one of the things we really got to make sure that we get right is what is on the nameplate and what is the vector configuration, and do we have that right? Because if we don't have those right, how are we going to get the proper results? How are we measuring correctly? So here's just a picture of a nameplate. Obviously, we have the high voltage side, 138 kV, and then we have the low voltage side. We can see from this picture that this is a delta Y configuration. We can also see that the Y side has an exposed neutral. And we also see here we have the DETC. We have our 5 taps, which is pretty basic in North America to have the high voltage tap changer or to have the DETC on the high voltage side and the OLTC or LTC on the low voltage side. But here we can see our 5 different positions. And here we can see the OLTC or LTC tap positions, as well as all the different voltages. So what we need to know about the vector configuration. The windings that can be tested against each other are shown here. We show them in parallel. So we know that H1 to H3 can be tested against X2 to X1. H3 to H2 can be tested against X3 to X2. And then H1, H2 can be tested against X2 to X1. I'm sorry, H1, H3 can be tested against X2, X1. X3, X1 can be tested against H1, H2. And this is actually a little bit different configuration. We'll see this is a non-standard configuration here. As we get in to this next slide here, we can see that there's a delta Y, and then we'll see some other different configurations that you guys probably see a lot more. So one of the things we want to know is, what is the angular displacement between our high voltage side and our low voltage side, or our primary or secondary? And so what we can see here from this vector diagram, we can see that there's an origin vector, which is the line coming out. It typically comes from the neutral and goes out through H1 or X1. And we can see this is where we can start to measure our displacement as far as what we can find out what our phase displacement is based on the configuration. So for this example here, we know we have a dy in 1. So we got a capital D, which refers to we have a delta on the primary or high voltage side, and then we have a y in, which is a y with an exposed neutral on the secondary side. Then we have a 1, and some people say, so what's the 1 for? And so each number correlates to a displacement of 30 degrees. So 1 through 11, excuse me. And so what we're looking at is you can actually take this vector and rotate it to where H1 is standing straight up, and then you could rotate X1 to be off to where those lines are in parallel, and what you'll end up is a clock position. So in IEC, you will see this more overseas, where they are actually able to clock it, whereas if it's at the 1 o'clock, that 1 would reference 1 o'clock. So H1 would be at 12 always, and then the low voltage side would be your clocking method, which 1 would be at 1 o'clock position, which would give you 30 degrees. So every time you move, so 2 would be 60 degrees and so on. So again, here's another dy. We can see this is where we start on the high side. This is where we start on the low side, and we determine what's the displacement angle here as far as degrees. And what we can come up with is 210 degrees of displacement between the high side and the low side. So this one would be a dy in 7. Again, when we're talking about phase voltage versus line voltage, again, on a delta, phase voltage is going to be equal to our line voltage. And then on a Y unit, our phase voltage is going to be different than our line-to-line voltage because we have to factor in the square root of 3, 1.732 because of the 3 different windings, or because you have a separation between your windings and neutral. So you have different voltages that you can measure. So in the olden days, you had to calculate this. You had your basic vector diagram groups, and then you had your calculation factor for based on whether you have a dy in 1 or whether you had a y in d7. You then had to configure so that you can convert your nameplate ratio. Nowadays, this is all done in most units nowadays, where this is automatically calculated for you, so you don't have to go through there. But if you need to, there's always reference material on how you can make sure that you're testing to the proper ratio. So again, we're back to the definitions. TNR was line to line. TVR is specific terminal of the high voltage to the low voltage. And TTR is the ratio between the physical number of turns. And then the MVR, again, we apply voltage, we measure voltage. It's the voltage that we apply. We are measuring on the other side, secondary, whether it's low or high voltage. And how does that apply to a nameplate? So let's look at it on a nameplate. So here we have TNR. We know that TNR is our high voltage side, our 138 kV, to our low voltage side, This is a Y, so our line to line, we know our line to line is 36K, 36.2K. So if we were to do the calculation, we would come up with a ratio of 3.81. Now there's some people prefer to do a TNR, some people prefer to do a TTR, which is proportional to the TVR, and it's just preference or maybe the standard that you're applying to. So then we see here TVR. Again, we're comparing from a high voltage side, a specific, to a low voltage side, and this time we're looking at the phase voltage, the line or the phase to neutral voltage here. So we have 138 kV to 20.9 kV. And then we have our TTR. Again, that's our number of physical turns to the number of physical secondary turns. And then we have our MVR. Again, that's our applied voltage, and then our measured voltage. So here we're talking about the different TTR testing techniques, kind of where we began. So those of you that are maybe familiar with the hand crank units, there's a lot of them out there still that they still do the job. They're great for difficult transformers where you have phase shifting or you have where you need to excite from the low voltage side. And so what we can see here is we have a hand crank, we have our connections on our transformer, single phase connection. We have our hand crank, and then we have a reference transformer. And we literally just crank this unit up, dial it in based off the knobs there, and what we're trying to find is with the null detector is a null position where we're not passing any current. We're still passing excitation current, but there's no current flowing between the reference transformer. And here's a picture of the TTR, the old hand crank unit. Of course, there's some limitations. There's also some advantages, and this applies to every test set out there. But if we're looking at this unit here, we know that the limitations. Obviously you got to manually balance it. You can only test one phase at a time, and then again, because we're reducing the voltage on the secondary or low voltage side, and we're measuring on the high voltage or primary side, we can see that there's obviously, depending on the ratio, there is a caution of safety here, because if we apply, let's say, just say 8 volts and it's 100 to 1, there may be a possibility that we could induce upwards of 800 volts on the primary side. There's also limited ratio range with these units, and the newer units, and you can get much higher ratio range. But this unit is very, and still today, a lot of people use this unit, but it's very easy to detect a problem, shorted turns. If you start to crank and your excitation current goes way up, then you'd be able to determine really quickly if there's an issue with the transformer. It's also a very accurate unit as well. So as we're advancing in technology, we kind of get away from the hand crank portion of it, and we started applying things like 120 volt input power. We started acquiring things like microprocessors, selector switches, even digital readouts, whether it's LED or things like that. We've got lights, we've got buttons. So here's a picture of an older unit. It's kind of got away from the hand crank style. We now have we still have manual phase selection. We don't have any automatic switching. There's no phase deviation. There's no ratio error. Literally, we can find out what our current is, and we can find out what our ratio is, but we don't have any way, without penciling it in, what our ratio error, and we can't detect any phase deviation. Advantages obviously is that it's a smaller unit than some, like in a factory where they would be testing. You would have a much larger unit because they need to have a much wider range. But with this unit and a higher voltage, with this unit you have a lower voltage, typically in the 100 volts, and you're exciting from the primary side, high voltage side, and measuring on the low voltage side. So there was that change from measuring or inducing voltage on the low voltage side. We've now changed in the 90s method. We changed to now inducing voltage on the high voltage side and measuring on the low voltage side. And so obviously some advantages here is we've got three-phase connection now. We have higher ratio measurements. We're more accurate on exciting current measurements. And then again, as I mentioned, we have the digital readout. Then we get more into today's method. Now we've got everything from onboard computers, embedded firmware, USB ports, Ethernet connection. Even some have thermal printers on them. You've got all the calculations and algorithms all built in. Again, we're still talking about doing the exciting on the high voltage side and measuring on the low voltage side. We still have the three-phase connections that we did in the 90s, but now we are able to do switching single-phase testing. So we're actually able to do an automated version of that. So everything becomes automated. We have test forms that do the automation for us. We have switching of the phases. We're able to test more applications easier without having to do shorts across windings and things like that. You can do phase shifting transformers, high voltage winding excitation. There's just some of the limitations there. Well, I'm sorry, the limitation there is a phase shifting transformer still is a little bit more complicated doing this unit. You do have to still make some changes as far as switching connections. But in the previous ones, you had to do shorting, you had to do flipping the connections, you had to do a bunch of different things. A limitation, but not so much a limitation. It's also kind of an advantage coming from the 90s to today's automated world is a switching method of doing your testing. You're still able to switch from one phase to the other without having to manually do that. But as we see, that becomes a limitation in the future. Advances, obviously, again, we have PC control. We can run it from our laptops. We've got lower excitation current and voltage. We have automated switching. And now we can actually see our phase deviation as well as a ratio error. And then we can even set up our own pass-fail criteria, and specialized reporting and all these things come with the automated world. So to look to the future, we go backwards in time here. We go back to a novel technique of doing step up or low to high testing, but we add something to that. We add, how about three-phase simultaneous? So before we had to switch, now we can do it. We can do the three-phase at the same time. Again, we're exciting from the secondary or even the tertiary side. We're inducing the voltage on the primary side. Of course, newer technology, you can set limitations on that so that you're not exposing safety concerns or things like that on the high voltage side. You can kind of set your output of your voltage to where you don't exceed that. Voltage dependence, and we'll talk about that in a little bit, but you can use this method is better with units that have higher voltage dependence because you're closer to the core. You can get more flux. You also have better coupling because you're on the low voltage side. There's a less excitation voltage required, again, because you're going from low to high, but because you lower the excitation voltage, you can raise the excitation current. But not all the time is a step up convenient, or is a step up the right fit for that transformer. There are some times where step up is not the best choice, and you can still get some errors that are slightly higher or may deviate from your step down process. So now, again, we're talking about looking in the future. We're looking at a true three-phase step down so that we can improve the testing of the phase shifting transformers, because we're inducing three phases of voltage at once, especially ones that don't have the exposed neutral. The standard actually doesn't require, but it speculates that it's better to use a three-phase than to do a single phase. You get increased productivity due to test times. Obviously, you're going to speed up your test time if you're doing all three phases at one time. It's a much faster process, and then you've got time to do other testing or diagnostics or things like that. Again, it's a safer practice to do step down. You're not having to worry about that high induced voltage on the primary side. And in some units, you may start to see tap changer controls and integration into these units. And in the past, it really wasn't an option. You still had to manually control the tap changer. But as we're going into the future, you're seeing more and more test sets that are starting to incorporate the tap changer control so that you can actually automate the process a little bit more. So the fun stuff is let's see we know here's where we've come from, here's where we're going. Let's kind of see what advantages are there to doing step up or step down, three-phase versus single phase. And we can see all that information here in the test data and test results. So first, let's start off with just a basic example of a test that was done. It's a DYN1 transformer. Again, how do we know it's a DYN1? We can see up here we have the diagram, the ANSI diagram number. We also have the vector configuration up here. And so if we were to look at the vector and compare it to the chart, we would be able to determine that there is a 30-degree displacement between the high voltage side and the low voltage side. That's where our DYN1 comes from. That's where our diagram number 5 comes from. They correlate together. Again, capital D for delta on the primary, or the high voltage side, YN for a Y with an exposed neutral on the secondary side. The 1 is for that 30 degrees. Again, if you go back to the clock method, 12 o'clock H1, X1 would be at the 1 o'clock position, which would give you the 1. Okay, and so we've got down here, let's go straight to the bottom. We can see that we've got our taps. We're testing nominal to nominal. We can see our voltages, what they should be based on the tap selection. We can see what our test voltage is. So here we're doing 80 volts. And as if we can look above, just above the actual TTR, we can see H1 to H3, X1 to XO. That's telling us that we're doing a step down method. So we're going from high voltage to low voltage. We can see what our TTR is, and we can see what our actual TTR. So that TTR, so right next to test voltage, TTR is the calculated TTR. So what it's basically stating is that it's using the information from the vector diagram, it's using the information from the voltage input, as far as what we put it right above it here in the primary and secondary, and it's using that to calculate the TTR. And so when we do the measurement, we go on to actual TTR. So now we have the actual TTR. So it measured the voltage and it compared it to the calculated TTR. And then we have our percentage of error. So here we can see that our percentage of error is the deviation from which the actual and the calculated are compared against each other. And so what was our limit? Our limit was 0.5%, and we are well underneath that at 0.04. Okay, right next to that, we have our excitation current. We can see that it's 0.5 milliamps of excitation current when we did this test. Again, we're doing it from the high voltage side to the low voltage side, so we know that the excitation current will not be as high as if we were to do it on the step up mode. Then we have the phase in degrees. So we talked earlier about the DYN1, this being a 30-degree displacement and phase angle based on your high voltage to your low voltage side. That is not what this is. This phase here is the deviation of that expected. So we know that when it does the test, it's comparing, is there a true 30-degree displacement? And this is the measurement. This is the result. So 0.11 degrees off. That's acceptable. Nothing in the standards that I'm aware of that tells you that there is a set point for this as far as how much deviation you should allow for. But obviously, if you had a high deviation percentage or degree, then you would know that there's an issue that will allow you to do further troubleshooting and do diagnostics. And again, if you were to connect it up completely backwards and do the test, you would have 180-degree out. So this would highlight red, and you'd be able to say, okay, yeah, there's an issue here. This is an example of OLTC, again, a load tap changer or on load tap changer. And just want to put this in here just for an example. You can kind of see every time you're changing your voltage, every time you're changing your tap, which when you change the voltage, you're then changing the ratio. And then you can see all the examples here and all the results. So voltage dependence, as well as, so when you're talking about voltage dependence on transformer, basically all transformers have some form of voltage dependence. And this is coming from poor magnetic coupling or a poor core, where you have say you have a delta tertiary and it may have a different rating of the other windings. You also have it's due to loading from the untested windings, and we have an example down here below. So we have an auto transformer with a tertiary, and the tertiary is a delta. So what we know is we're applying to the high voltage side, and we're measuring on the tertiary side. And the issue here is a Y delta. So if it's a delta Y, there wouldn't be a huge issue here. There would still be a dependence, but it wouldn't be as high, because what we're doing here now is we're getting the effect of the loading of the tertiary delta, because now because those connections are in series, we know that those are now accumulating some of that voltage that was induced, and that can slightly affect the ratio result. And so another thing to note here is a lot of times when you're doing a test, you may select auto voltage, or you may select, let's just say if you're doing high voltage side to low voltage side, maybe you selected 8 volts or maybe 40 volts. And as you notice, sometimes if you increase that voltage, you can get past that voltage dependency and you can get better results. And we'll get a little bit farther into that as we go. So another different transformer configurations that like we said earlier, can show you a little bit higher voltage dependence than other transformers. Obviously, auto transformers with tertiary windings that are delta could be an issue, as we saw earlier. We have delta on the secondary. Again, as we talked, if we're doing a high voltage to low voltage, here is another example where we're going to get that loading on the secondary side. And then we have the 3-winding transformer, where we have a delta on the tertiary, delta on the high, and a Y on the low side. So again, all transformers have some form of voltage dependence. It just depends on the configuration, whether it's going to be slightly higher, and it may affect your ratio result. And so here's an example of doing the different test voltages. And so again, we see primary excitation voltage. So we know this test was done from the high side to the low side. And as we can see, if we started out with 8 volts, we can see our ratio error is 0.73%. So we're outside of that tolerance limit. So this would be, we'd have to either do further troubleshooting or find out why it's at 0.73, because our tolerance is 0.5. But if we increase the voltage to 40 volts, it goes down. 80 volts goes down. When we get to 125, it's down way below the acceptable level at 0.1%. And this comes into effect again, as we mentioned. All transformers have some kind of voltage dependence. It's going to come down to what it's going to take to require the right amount of flux. So we know of voltage dependence, and we know that it's an issue, and so we got to figure out how can we get past that. What are some solutions that we can utilize that can help us with voltage dependent transformers, and be able to get better results. And so one of those is use a 3-phase source. And as we mentioned before, there's a difference between 3-phase switching, and there's a difference between true 3-phase simultaneous source. We can also test using phase to phase versus phase to ground. Obviously, this applies if you're on a neutral configuration. I'm sorry, a unit with a neutral configuration, such as a Y with a neutral, and you can do phase to ground if you wanted to, but you can also do phase to phase. And if you have a Y transformer that doesn't have an exposed neutral, then obviously phase to neutral or phase to ground either wouldn't be an option or would not be the request or the recommended option. You would want to do a phase to phase test, and we'll see some results here in a minute and kind of see how that goes. Again, you can do the test from the delta winding. So we talked about doing a delta on the primary or the high voltage side and a Y on the secondary side. We will get the loading on the primary side, but we're measuring on the low voltage side. So when we're measuring on the low voltage side or the secondary side, if it's a Y on that side, then we'll get a better result. But if we were to have that same configuration backwards, where we would have a Y on the primary and a delta on the secondary, we're going to get that loading on our measurement portion of it, because we would be doing a step down method. So an option would be to do a step up method in this case, and now you're testing from the low and measuring on the high. So you're inducing on the low voltage and you're measuring on the high voltage. Now you're getting past the issue because you're measuring on the Y side and not on the delta side. And of course, if you could apply the voltage to the winding that's closest to the core, you're going to increase your excitation. You're also going to optimize your magnetic coupling and things like that. So what we talked a lot about step up, step down. So what is step up? What is step down? It's very basic. It's just step down as you're applying it to the primary. Again, as I mentioned, primary here, I mean high voltage side, and then we're measuring the voltage on the secondary or tertiary. And then step up is the opposite. We're applying the voltage on the low voltage side or the secondary side, and we're measuring it on the primary side. So how does that benefit us? What's the big deal with whether you do it on the low voltage side or the high voltage side? And so here we have a couple of results here. We can see that this is a YND, and we're doing primary excitation. So we're doing a step down. And we talk about phase to neutral. We're doing a phase to neutral test. We can see in the blue there. And when we have our tolerance level at that 0.5% set there with the red line across, you can see there's a couple, like on C phase, A, B phase are fairly close to that, but C phase is out quite a bit there when we're doing a phase to neutral. And this test is done with 40 volts. And so if we change it from doing a phase to neutral, we can see by utilizing one of our solutions, we can see that phase-to-phase excitation, we are lowering that percentage of error and we're getting a better result. So how about step down versus step up? Here we can see the excitation. We're doing the comparison of the step down versus the step up. So we have the step down is in green here, and we can see on A, B, and C phase that we're within the tolerance of 0.5% error. But what we notice is if we switch over to a step up mode, we can see that single phase on both of these tests, we can see that applying at 8 volts, we're closer to the core, to the winding that's closest to the core. We're getting higher excitation current. We're also getting a higher amount of flux. So what we see here is now our ratio has really dropped down as far as on the error percentage, and we're down to 0.1 or lower. So here we can see some more examples of testing phase to phase versus testing phase to neutral. So on our first example up here, we just want to highlight that we have a test voltage of 8 volts on the first test, and then we increase that to a 40 volt test. Of course, now we're talking about step down method for both of these examples here. As you can see right above where your percent error is, you can see the connection diagram. So it's H1 to HO, and we're measuring on X1 to X2, applying on H1 HO, measuring on X1 X2, and we can see our percentage error. As we increase the voltage, our error percentage went down across the board there, and we've gotten closer to acceptable tolerance limits. So what we then say, okay, well, what if we do this test again, but we do it phase to phase? So now you can see our connection is, instead of H1 to HO, we're doing H1 to H3 and X1 to X2. So we're doing phase versus phase to phase, or line to line versus the phase to neutral or phase to ground. And so again, we apply our 8 volts, and we are real close. We're at 0.49, 0.5. We're right on the line, very close. And then so if we if we step that voltage up now to 40 volts, we can see now our ratio percent error has dropped even more. So just a comparison of doing phase to neutral or phase voltage test versus a line-to-line test. You can see the difference there. With the increase in voltage, you can see a difference even more. So here we can see a secondary inducing voltage on the secondary side and measuring on the primary side or high voltage side. And so what you can see here is we have an example of the two comparisons. First we have a step down, and here's our ratio percentage error, the 0.33%, 0.371, and 0.473. So we're within the limits, we're within the tolerances, but we're very close, especially on C. So what we then do is we convert over and use the old hand crank TTR and we do an 8-volt step up. And now you can see how our percentages went way down as far as on our error. And so now that we're way within tolerance at this point. So what does increased excitation current do for us? Well, if we're doing a step up mode or from low to high, we can see that this is allowing obviously for more excitation current. When you have more excitation current and more flux and better magnetic coupling, you are able to use that information because you have much more sensitivity, which allows you to detect fully or partial shorted turns and even some core problems. Because like if you're winding during transportation or something like that, it gets damaged, or you have a through fault or something like that, and if that winding moves away from the core or closer to the core, this is going to change your results when you do the tests. So easier to detect. Again, we can easily detect full or partial shorted turns. And again, on the core problem, we can see that if we're trending and our excitation current goes way up or way down, depending on our configuration and depending on our results, we can then use further diagnostic tools to find out, okay, did something happen? Was there a through fault? Was something shift, something move? So we talk about more flux with less voltage because we're doing it on the low voltage side, stepping up to the high voltage side. So here we can see some results from a unit with a tap changer, and in the extreme of 1, which would probably be 16R, we can see that we're a little bit above that acceptable limit at 0.51%. And so what we do is then we do the test with a step down, and we can see, a step up. We can see with 250 volts induced into the transformer. So based on whatever your ratio is and configuration, the voltage that's applied to the low voltage side, secondary side, then induces up to 250 volts on the secondary side, and this obviously for safety reasons, because you don't want to have 800 or 1,000 volts on the primary side. So here we can see, just by example, our percentages went way down because we've got more flux, we've got higher excitation, equals more sensitivity equals a better result. So here we have an example of single phase versus 3-phase excitation. And we can see that there's just a simultaneous test. So when we were talking earlier about doing simultaneous tests, talking about doing a true 3-phase test, here's where we can see the results from what it looks like when you do a single phase switched versus a true 3-phase excitation. And so the true 3-phase is in green here. We can see our percentage error. None of these are exceeding the error. But what we can see, though, is we're getting better clarity and better results by doing the 3-phase versus doing the single phase. Single phase is kind of all over the board here based on the voltage. So the first one is 3 volts, next one's 6 volts, then 12 volts, and then 15 volts. And so what we can see here is that there's a drastic difference between doing the 3-phase versus doing the single phase. And any inequality in the magnetizing characteristics of the 3-phase can result in a shift of the neutral and thereby cause unequal phase voltages. So when such an inequality is found, the connection should be changed either to a delta or a Y. Now, what we're talking about is if we have a Y transformer without a neutral exposed, three-phase simultaneous phase testing is the best way to go because of that inequality in the magnetic characteristics of the unit. Yeah, okay. Let's go to the next slide here. Thought I had a couple more points on there, but we'll just go ahead and go to the next slide here. Three-phase, again, we're talking about 3-phase switch versus 3-phase simultaneously. How does this help us? We reduce test time, again, because we're testing 3 phases at once. We're not having to wait for the switching portion of it. We can see that we can drastically reduce our test time, especially when you're talking about OLTCs. And you can see here, just for an example, how much quicker you can get if you're using 3-phase simultaneous versus just doing single-phase switching. So again, how does that help us? We have extra time that we can do additional tests, test additional assets, things like that. So where do we get some of these sources of error? Again, we refer back to the how the transformer is designed and how it is built. Obviously, we have our high voltage winding on the outside, low voltage winding on the inside. We have press board, we have space, we have oil, we have the core, all these things. So depending on the design, you can see errors higher on a step up, on the step up method, but they've been found to be marginal. So just to say that just because you have a step up method or you're using step up method doesn't mean it's always the right choice. Step down may be the right choice. Again, we're going back to design, we're going back to characteristics of the unit. Especially like on pad mount transformers, you may have the spacing obviously between high voltage and low voltage is going to be different. It's usually much closer. And then you've got different permeabilities and you have different coupling. So here we can see where a three-phase simultaneously versus a three-phase step up. And so what we can see here is our ratio error of our three-phase simultaneous step up is better than whether we do the three-phase switch. But they're not that different. They're not that extreme off that you'd be like, oh, well, this is not the right method for me. This is just a comparison to show you that three-phase simultaneously, depending on your configuration, can get you results better or maybe very comparable to your three-phase switch. But there are also different methods for whether you're doing step up or step down is going to determine what your results will be. So in summary, we'll just say that obviously TTR is it's a very easy test to do. It's a very basic test. It's done at commissioning and it's done at out in the field during maintenance. When we're talking about DETCs, we typically do the DETC once it's in service. We leave it on the tap that's in service, so we do the test on all the taps on the OLTC. In a commissioning method, we would do the test on all taps. Three-phase transformers are typically tested one phase at a time, along with the automated switching option. When we also looked at doing three-phase transformers with a three-phase simultaneously test. And then, of course, when we talked about voltage dependency, we talked about the characteristics of the voltage dependency as well as some different techniques to overcome that. And so now we'll look at some different Megger instruments that we have available to do TTR or turns ratio testing. And so here in the picture, we've got a couple different units. We've got a TTR 300. We also have a TTR 330 with the screen, so you can get with the screen or without the screen. I think one of the really good features about this is the connections for the cables. You go up, make all your connections one time, and then you can, each phase is separable. So you connect what we call umbilical cord to the unit. You take all the cables up on top of the transformer. You make all your connections. And then you drop down your lines and make your connection down at the ground versus having all your cords and your umbilical cord all connected in one. This is going to help you with troubleshooting. It's going to help you with, if you don't need to use that phase, you don't have to connect it, things like that. As well as that jaw is expandable. It's a Kelvin clamp, so you have both your voltage and your current measurement on the same clamp. And then we have the MWA. It's a combo package. So the MWA will do both, is what we call our Megger winding analyzer. It will do both TTR and winding resistance with this, again, utilizing one connection on the transformer. You can switch from test to test without having to go back up on the transformer, which is going to save you time and as well as safety. And it can be ran off PowerDB. Talk about Trax. Trax is kind of our, what we like to call it, all-in-one box. It does a lot of different testing for one unit. It's substation testing, everything from CTs. You can do power factor. You can do excitation current. You can do a lot of different things with the circuit breaker testing. TTR, winding resistance, even a DLRO. It's a multifunction unit. Obviously, with one unit, depending on the accessories, there's a ton of different accessories you can add to this. Like for one, if you want to do power factor, there's a box you can add to it for the 12 kV, and there's switching boxes. There's a lot of different capabilities of this unit. It's definitely state of the art. And we got coming soon. This is going to be released very, very soon. But we have a true three-phase transformer turns ratio meter. This is a true three-phase unit that you can do both step up and step down mode. Very quick, 8 seconds testing. And it's very useful for doing anything with phase shifting or zigzag. You can do it very quickly and very accurately. Okay, Jamie, I'll turn it back over to you.
All right, thank you very much, Aaron. At this time, the presentation portion of the webinar is officially concluded. We will now, or in a few moments, take 30 minutes to answer as many of your questions as possible. So if you have any questions, you haven't submitted them already, please do that now in the Q&A box on the right side of your screen. For those that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple minutes to provide your feedback so we can continue to improve upon future webinars. And on the survey, just be aware there is a field where you can also request a demo or quote on any Megger products. Also, a reminder, a copy of the presentation along with a link to the video recording of the webinar will be emailed to everyone within about 2 business days. And you can also view recordings of previous webinars on our website at us.megger.com/webinars and register for next month's webinar, Directional Overcurrent Relaying Now and Then. And the presenter for that presentation will be Mohit Sharma, Megger Relay Application Engineer. All right, now let's go ahead and get to some of your questions. The first question, attendee Glenn asked, what are your thoughts on operating the tap changer where the tap changer has not been operated for several years? And part 2 of that is, should the TTR only be performed at the current tap?
Okay, I'll take that question. Good morning, this is Diego Robalino. Typically, when you are in the field, one of the key questions is, do I run the TTR on every position of my de-energized tap changer, or do I just run on the position where I found the tap changer? I would suggest you ask this question to the owner of that transformer. What does he want? And if he says that the DETC has not been exercised in the last few years, then your suggestion should be, hey, maybe we don't move it, because as soon as you move that tap changer, you make it into more trouble than help. But if the owner of the unit still wants that tap changer to be tested, then you make a little paper saying that you recommended not to move it, but it's his request. So you cover yourself somehow. So basically, just to summarize, the answer is, if the de-energized tap changer has not been exercised for several years, it does require some mechanical maintenance to be done. With that being said, when the mechanical maintenance has been done, you are safe to test it. If it's not, then you may get in trouble. So be aware of that. And if we're talking about LTCs, then LTC typically is being tested on, especially on the position of operation, right? And in the range where the tap changer is moving up or down. So just keep this in mind.
All right, thank you, Diego. Next question was asked by Alexi. For routine maintenance testing of transformers, do you recommend doing a 3-phase test only, single-phase test only, or perform both?
Yes, I will take that one. Well, in reality, it comes down to what you have available, right? I mean, you don't have to do both if you have a 3-phase unit, which to be used. So if you can do a 3-phase test, it will save you some time. And again, I mean, it's really irrelevant. You can do 1-phase, 3-phase. The results should be the same if you follow the procedures that Aaron explained. So again, just to summarize, if you can do 3-phase, just go ahead and do 3-phase, and you will save some time.
All right, thank you, Daniel. Next question is from Vinkata. What is the recommended testing frequency of TTR on a 15 MVA transformer. Part two of the question is once every 3 years sufficient based on recommended standards?
Okay, I'll take that question. Interesting to ask about the frequency of testing, right? You may not have time to test your transformer. You may not have the opening, or operations will not allow you to do the testing on the frequency that you may plan to do it. But the only reference that I can suggest you to look at is the NETA MTS, which is the maintenance testing specification. And if you look into this document, there's Annex B, where it will show you the frequency, at least the recommended frequencies for testing any piece of equipment. Now, the question is not about 15 MVA or 150 MVA. The question is about criticality. How critical for you is that 15 MVA? If that 15 MVA is the power source for a hospital, then it is critical, right? If that 15 MVA, I remember somebody saying, I do have quite a few distribution transformers in my network, but the one that feeds, the governor's house, that is the most critical one. So just think about the criticality of the unit and look at the standard. There is a reference. You can evaluate based on this information and decide what will be the most suitable frequency. One of the things that I would suggest you guys is whenever you have a fault, this is one of the easiest testing techniques to determine if that transformer is still alive or not. So keep in mind.
All right, thank you, Diego. Next question. Are there any temperature dependencies or correction factors to be considered while performing TTR?
No temperature dependencies. Now, correction factors, if we go back to Aaron's presentation, depending on the configuration, the connection configuration of your transformer, you do need correction factors. And I don't know if that's what you were asking. But again, no temperature dependencies, but just you need to be aware of what is the correction factor for that connection configuration, as the calculated TTR value that you get is taken from the nameplate values, right? So if you do that calculation straight away, again, you would need that correction factor depending on the connection configuration of your transformer.
All right, thank you, Daniel. Next question was asked by Abundio. When testing phase to phase, like for a Y to D, and is there no HO connection, or can it be done?
Yeah, so we kind of went over, there was a couple examples there where we had some transformers that did not have the neutral exposed or available. So obviously it's a little bit harder to do a phase to neutral test if you don't have the exposed neutral. So the best method for that would be a phase to phase test. The even better method for that would be to do the, as we mentioned, the three-phase simultaneous testing, because that's going to give you your best result.
All right, thank you, Aaron. Next question. Do transformer manufacturers typically specify recommended test methods, like step up or step down, based on their design and configuration? Part two is, if not, how do you determine this? Would you recommend just doing both if we don't have a specified test method?
Okay, so for the first part, do the transformer manufacturers would give us our recommendations? Typically, no. They won't tell us if it would be better, like you said, because of the design, to do step up or step down. So usually, I mean, nowadays, most instruments in the market will do a step down method. And again, just going back to Aaron's presentation, is because in terms of safety, it's just easier to just step down the voltage, so we know that what would be the maximum voltage that our TTR instrument should be able to handle. Now, for some transformers, for example, when you have a voltage dependency because of the design of the unit, it will be better to do a step-up test. And now, how do you determine that? Well, again, if you test your transformer and you get results that are outside the acceptable criteria from IEEE, the 0.5% from the nameplate value, then you might want to try either doing a step-up test or a higher voltage test.
All right, thank you, Daniel. Next question was from Granyard. Why do we have some test results with an error or negative?
Yeah, so there were a couple examples in there where you could see that the ratio or percentage error was in the negative. That means that whenever the test was done and the results came back, the ratio was determined to actually be less than the nameplate voltage ratio, or nameplate ratio. So you can see that it would go negative versus a positive. So as it goes positive and it gets higher in error, it means that the ratio is not as close to the nameplate as specified. It's much higher. Also, there was some other negatives in there as far as on the deviation from phase displacement. So it's just giving you the deviation from your expectation of the 30 degrees displacement, but it may be like 24 degrees or it may be 36 degrees. So that's where you're getting that negative, whether it's lagging or leading.
All right, thank you, Aaron. Next question is, what, if any, advantages are there to doing a high voltage TTR test voltage up to 10 kV, especially on EHV transformers, 500 kV or 500 MVA?
Okay, that is quite an interesting question because time-wise, you will be really frustrated doing a single phase capacitive ratio, applying 10 kV through a capacitor system, and typically you will use your power factor test set to do that kind of test. But with that being said, even though time is an issue, the only advantage that you have is that if you have any potential damage on the interturn insulation of your transformer, you will never see it with only 100 volts that you apply on a ratio test set. But you may see it with 10 kV. And you might be able sometimes, maybe you can maybe even see the deviation or may create further damage and maybe, break up the insulation that you have on the interturn system with 10 kV if there is potential for damage. So that is really the advantage that you have when you're doing a high voltage ratio test. Not because of time, you're really not into the accuracy of the ratio test. You're really looking into the interturn insulation with that higher voltage.
All right, thank you, Diego. Next question was asked by Robert. What would cause the phase angle shift or error in the measurements?
Okay, excuse me. This is actually a little bit related to a previous question asked on the error, the negative error on the results. And both of these have several factors that affect, and one of them is caused by the voltage that you use to run the test that will change the coupling between the two windings of the same phase. Again, that angle shift that you get in the results, comparing what you're measuring against the voltage that you are applying, again, that same phase of the transformer.
One thing that we
go ahead.
One thing that we could add on that as well is you remember that basically the construction of a typical transformer, let's talk about a core type transformer, right? You will have your low voltage closer to the core, and then you have the high voltage on top of that low voltage. So basically, construction-wise, your angle should be 0 or 360 degrees, or if it is in the opposite direction, should be 180 degrees. But what is interesting here is if for whatever reason the geometrical construction of your transformer has been changed because of a fault, because of the transportation, because of whatever thing, and the position of your winding may have changed, that may create also some phase deviation and angle with respect to the original. So it is also important to look into this.
All right, thank you guys. Next question was from John. Should you order contractors that do testing often to get better results?
So when you get your test results, and what I'm gathering from this question is, should you order contractors that do the testing often to better results? So if you get a result that say it's 0.49%, but you think that, oh, well, maybe if we use a different method we can get a better result, or something like that. Typically, I would say that if it's within the tolerance of 0.5%, then I would say that the unit is passable. But if you were outside of that limit, and say you were in 0.56, and then the contractor was to give you those results and say, okay, here we did the test, but this is what the answer was, then we would have to say that. Are there other options to do different tests to get a better result than there are, whether it's a step up or whether it's a three-phase simultaneously? If you have the ability to do those tests to get better results, then that would be the better choice. Whether you tell them to make sure they always get the best results, they should always be striving to get the results that meet the tolerance specification based out of NETA or IEEE.
All right, thank you, Aaron. Next question is from David. Have you seen a lot of situations in which the same equipment has been used on much smaller low voltage transformers, like a standard 75 kVA unit with 480V delta primary, 208Y/120V WYE secondary?
Okay. The same equipment, basically the way that the equipment works is you apply voltage on one side of the transformer, you measure voltage on the other side. We've been talking here during this presentation about step down, which means applying from the high voltage side to the low voltage side, or step up, applying from the low voltage side and measuring on the high voltage side. But one important thing that you need to understand on this process, for those who are not familiar with the step-up process, is that the voltage that is being applied on the secondary winding is regulated with the measurement of the voltage on the high voltage side, okay? That way, you do not exceed a maximum voltage that is it's the limit for the testing methodology equipment that we have inside, and it's safe for the environment, where you are testing. With that being said, the equipment for ratio testing can be used on high MVA transformers, little MVA transformers, right? I think that a transformer, unless you're getting into some special applications of transformers, higher frequencies or different things like that, electronics, right? But for electric power system application, yeah, the equipment is basically the same. The principle is the same. We apply voltage, we measure voltage.
All right, thank you, Diego. Next question was from Kenneth. How do I know if it is safe to test a transformer as a step up? And then part two of that is, from the presentation, it seems like this is the more accurate way, but what determines if this is going to damage the equipment or not?
Okay, that's a good question. Usually when the TTR instrument that you have has the capability of running the step-up test, the unit itself would do a pre-check of the transformer with a smaller voltage to to see what the ratio of the transformer is, and then adjust the applied voltage for the test, again, just to make sure that the voltage levels on both sides are okay for the unit to be handled. So the unit itself, again, you need to have a unit that is capable of running those tests, and those units will have the provisions to determine what is the best voltage to run the measurements.
All right, thank you, Daniel. Next question was asked by Anthony. When performing an OLTC excitation test, should you test all 33 taps?
Okay, when you go back to the OLTC test, when we determine between the DETC and the OLTC, if I'm looking at this question correctly, they're just asking every time they do the turns ratio on the OLTC, should they always do all 33 taps? And the answer is you should always do all 33 taps, because you don't know what the extreme ends could be. If they're different, you don't know what, if individually, if you have there is a fault in between one of the phase or one of the taps, whether you have an issue with the tap changer making it all the way from one end to the other. So the best practice is for IEEE and NETA is to test all of the taps on the OLTC, but as far as concerned on the DETC, most people during commissioning will test all of them, and then once the unit's in service, only test the one that is left in service.
All right, thank you, Aaron. Next question, Kent asked, with such a wide variety of results between single phase, three-phase, step-up and step-down test configurations, if you try to compare to previous testing trending, how do you correlate results?
Well, in reality, all those measurements, I mean, no matter how you made them, either single phase or three-phase, or with the step-up or step-down method, they all should be comparable. In reality, I mean, and usually the report that you get from any TTR instrument will not say that, okay, we use the single phase or three-phase method to run these measurements. Again, because all those values should be comparable to each other, irrespective of what method you use to take those measurements.
All right. Thank you, Daniel. Next question, how are you expected to proceed with TTR testing for a dry type transformer without vector group stated on nameplate?
So one of the things you may run into is if it doesn't have an actual nameplate on there that has maybe a vector group or even the configuration in there, and so you kind of have a couple of problems here. One of them is if you just guess and you just say, oh, well, it looks like a DYM1, or it looks like X, Y, or Z, whichever configuration you pick, you're going to run into, because you don't know the full characteristics of it without the drawings, without the actual nameplate, you could run into some issues where you think you may know exactly what it is, but you may run into a problem where when you test it, it fails, but it didn't fail because it's actually bad. It's because your connections were incorrect. So unfortunately, when it comes to there's nothing available, no nameplate information, no nothing, you can look at your connections and you can base it off of your knowledge or your experience on if the connections are even marked. You can use that as an example. You can test it that way. Another thing is like even with the let's say a pole type mount transformer, it has oil in it, but you can open it up and verify the connections inside. Also, there's issues with if you don't know what the configuration is, you can think that you're doing a step down and you may do a step up, and there's a safety issue because now you have conducted a test on a unit that you thought you were doing step down and now you're doing step up. So there are certain test sets that have, and we have those as well, that where you can determine the vector group, which is a nice tool if you can utilize that on that transformer, where it will try to determine the vector for you. But again, it goes back to if you don't know the full characteristics of the transformer, you need that information because there may be something you don't know about, some kind of internal grounding or something where you could either damage the equipment or injure somebody. So unfortunately, it's always best to have that information. If you don't have it, result to people that have experience with testing these time, find one that's like it. If you can use the vector find. Again, that comes back down to safety, whether you may in fact do the test incorrectly or test the unit in a step up mode when you didn't mean to.
All right, thank you, Aaron. Next question. Why is the ratio not able to detect on LTC preventative, auto transformer, wrong polarity, or cross lead connection?
Okay. I'm not quite sure if the question is related directly to the LTC. If you have a reactive LTC, basically you're testing right now the transformer windings itself, and you're injecting your high voltage to low voltage or vice versa. Although you should be able to verify if there's any wrong connection of your LTC, you may get a different angle on the deviation and different ratios. So that will be the only thing. I think that whoever posted this question, we would like to clarify exactly what is he referring to.
All right, thank you, Diego. Next question, should the same test method connection not be repeated for periodic testing of a transformer in order to enhance comparison between tests?
Not necessarily. Like we discussed in the previous question, I mean, connections-wise or the method that you use to take the measurements should not affect in a way that you will get different results. So it's actually, I mean, it's very typical, right, that whoever is running the test is going to use the same instrument to run the measurements the next time that transformer is up for maintenance. So not necessarily you can use the same connection, the same method to test that unit.
All right. Thank you, Daniel. Next question is, for just TTR test, how much isolation of the wiring connections to primary and secondary sides are required for most accurate results?
Obviously, for the most accurate results, and typically this is a recommendation across the board, is you want to disconnect anything coming in is on your load side and anything coming in is your main on your primary side, because not only most people when they do TTR, they don't just do TTR. They're just like, oh, we're just going to go do TTR. They're going to do a bunch of different tests, whether it's power factor or any of these tests, insulation resistance, and all these tests require that you have to isolate your load from your primary incoming voltage. And this is also, you don't want to do the test on a transformer with the wires still connected, because you can induce voltage into things that you don't want to. It's also, again, it's a safety risk of people down the line.
All right. Thank you, Aaron. Next question is from Anthony. When using different TTR test sets, will you get the same results or can they differ?
Well, unless you have one of those special cases where your transformer, for example, could have a voltage dependency for a TTR test. If you are using two instruments that the one was using 40 volts for the test, the other was using 200 volts. And again, if you have one of those special cases when having a transformer with voltage dependencies, you will get different results. But otherwise, you could use any instrument, and again, any method, step up, step down, you should get the comparable results.
All right. Thank you, Daniel. Next question was from Randall. How will testing differ between subtractive and additive transformers?
Okay. The first thing is, when you come out to the field you need to look at the nameplate of the transformer. And the most important thing using especially this three-phase connection type instrumentation is to make the right connection to the right terminal. If you go on a typical transformer, which is the subtractive type, you will see that your basically your XO is in line with your HO, your X1 is on your H1, X2 with H2, X3 with H3. But when you are on an additive type transformer, the location of those bushings will be the opposite. So just make sure that you understand that you do your right connections, and then again, it's voltage applied from one side, voltage measured from the other side. That's all it is.
Thank you, Diego. Next question was from William. For acceptance testing of medium voltage dry type step down transformers with manual tap changers, do you test the complete manual tap range or just the as found test?
I would say if you have the ability to test all the taps, that's the best thing to do. If they're referring to in manual tap changers of breaking the connection and making a new connection to a different part of the winding to get a different ratio, again, on acceptance testing, it's always best to do all of them because you never know whether they're going to leave it in that connection or whether they're going to change it later down the road. So for acceptance testing, if possible, the best way to do it is to do all of them. And then, of course, in maintenance portion of it, you would just do just the one that it's connected to.
All right, thanks, Aaron. All right, it looks like that's all the questions that we have for today. There were a few other questions that we weren't able to answer that we figured would be better answered offline, so we'll be following up with you on those questions over email or by phone in the coming weeks. But those are all the questions that we felt were the best to be answered today. We want to thank you all for attending, and remember to please fill out that survey if you get a chance. We really appreciate that. I hope this was a great webinar for everyone, and thank you again. Have a great weekend, everybody.